You know the periodic table, right? For most of us, it's just this giant chart of elements we were forced to memorize. But what if I told you it's not a list, it's a map? A logical, coded map that once you get the rules, tells you exactly how every single element is going to behave. Well, today, we are decoding it.
So here's our game plan. First, we'll decode the basic rules of the map. Then we're going to use two really simple but powerful analogies, I call them the snowman and the magnet, to get a handle on atomic size. We'll uncover the golden rule of shielding, solve the mystery of the reactivity flip, meet some fascinating rule breakers in the middle, and finally, I'm going to give you the golden thread that'll help you explain any trend you'll ever see.
Okay, first things first. The way this table is laid out, it is not random at all. It's a super deliberate structure based on the very heart of an atom, and we're about to crack it open right now.
It all boils down to one simple number, the proton number, or what you might know as the atomic number. As you move from left to right one little step at a time, you're just adding one more proton to the nucleus. That's it. That's the master rule that controls everything else. And this simple arrangement gives us the two main rules of our map. The horizontal rows, which we call periods, tell you exactly how many electron shells an atom has. And the vertical columns, the groups, tell you the number of electrons in that outermost shell, its valency. Shells and outer electrons, that's the code. Simple as that.
All right, so let's use that code to check out our first and honestly most fundamental trend, atomic radius. Or in plain English, just how big is the atom?
Just look at the difference here. On the left, as we go down group 1, the atoms get way bigger. It's obvious. But on the right, as we move across a period, they actually get smaller. Wait, what? How does that make any sense?
Okay, here's the why. When you go down a group, you're adding a whole new electron shell every single time. I call this the snowman effect. You know, you're building a snowman, you keep adding bigger and bigger sections. More shells means a bigger atom. But when you go across a period, all the new electrons are in the same shell. What's changing is the nucleus. We're adding more protons. This creates a much stronger positive charge, and it acts like a stronger magnet, pulling that outer shell in tighter and tighter. More pull, smaller atom.
Now let's talk about the concept that truly unlocks everything else, electron shielding. If atomic size is the what, then shielding is the why behind pretty much every other trend we're going to see.
So think of it like this. The electrons in those inner shells create a kind of screen. Because they're also negatively charged, they kind of push back against the outer electrons and block or shield them from feeling the full positive pull of the nucleus. It's like they create a bit of static or fog between the center and the edge.
And this right here is the crucial difference. As you go down a group, you're adding more shells, which means you're adding more and more screens. So shielding increases a lot. But when you go across a period, the number of shells stays the same, right? So the amount of shielding stays pretty much constant. This one idea is the key to understanding reactivity.
Okay, so let's use what we just learned to solve a big puzzle. Why do the metals over on the left side of the table behave in the complete opposite way to the nonmetals on the right when it comes to reactivity?
I mean, this is the central question, isn't it? As you head down the table, metals get more and more explosive, but nonmetals get calmer, less reactive. It seems like a total contradiction, but don't worry, shielding and size give us the perfect answer.
Let's break this down. Look to the left. These are the metals, the givers. They want to react by losing an electron. Now, as you go down that group, the atoms get bigger and they have way more shielding. This means the nucleus has a really weak grip on that lonely outer electron, making it super easy to just give away. That's why potassium is so much more explosive than lithium. Now look to the right, at the nonmetals, the takers. They want to gain an electron. And here, being small is a huge advantage. Fluorine, right at the top, is tiny with very little shielding. Its nucleus has this powerful focused pull, and it can easily snatch an electron from something else. But look at iodine, way down at the bottom. It's huge. It has so many shells shielding its nucleus, it can barely feel the outside world, let alone attract an electron.
So let's shift our focus to that big block of elements right in the middle of the table. These are the transition elements, and, well, they kind of play by their own set of rules.
First off, they're just physically different. Unlike those soft group 1 metals you can literally cut with a knife, these are what we think of when we say metal. They're hard, they're dense, and they have really high melting points. But their real story, the interesting part, is their chemical versatility. Chemically, they've got 3 superpowers.
1, they form these beautiful, colored compounds in solutions like that classic blue copper sulfate. 2, they have variable oxidation states. That just means they can form ions with different charges, like how iron can be both a 2+ and a 3+ ion. And 3, they are fantastic catalysts, speeding up all sorts of crucial industrial reactions.
All right, let's pull all of this together. I'm going to give you a simple but really powerful strategy to explain any periodic trend you are ever going to come across.
Okay, this table puts everything on one screen. Let's just do a quick review. See that top row, atomic radius? We know it decreases as you go across a period, but it increases as you go down a group. Now for reactivity, remember that crucial split. For metals, on the left side of the table, reactivity increases as you go down. For nonmetals, on the right, it's the total opposite. Reactivity decreases down the group. It all comes back to size and shielding.
And this right here, this is the golden thread. If you want to really nail this stuff or get top marks on an exam, you have to use these 3 key words in your explanation. Number 1, nuclear charge. How many protons are in the nucleus pulling? Number 2, distance from nucleus. How many shells are there, making the atom bigger? And number 3, shielding. How much are those inner electrons getting in the way and blocking the pull? With these 3 concepts, you can explain absolutely anything.
So, you see, the periodic table isn't just a list of facts to be memorized. It's a system of pure logic. It really is a code. We've just unlocked the basics. So the real question is, what other secrets are you going to discover hidden inside it?